Welcome to today's Explainer. We interact with digital block-based worlds all the time, right? But today we're pulling back the curtain on the actual architecture running underneath. We're going to look at Minecraft not just as a game, but as a rigorous, fascinating mathematical system.
So what happens when the math of a video game universe just breaks? Well, before we can understand how a digital universe collapses into total chaos, we first have to explore the perfect, deterministic geometry that builds it from the ground up.
Here's our roadmap for this explainer. We'll start with the primitive voxel. Follow it through the graphical pipeline. Check out how the system optimizes millions of polygons. And finally, witness the absolute limits of 32-bit math.
All right, part 1, the math of the voxel, the textual foundation. Let's strip away all the visuals and look at the absolute base of the world.
At its core, a block in a voxel engine isn't a physical object at all. It has no mass, no actual shape. It's really just a textual instruction waiting to be interpreted by a machine, a highly precise spatial text vector serialized as raw numerical data.
All this spatial data is stored in what are called NBT, or named binary tag files. Now, the system uses highly accurate double-precision floating point numbers to pinpoint exactly where an entity is. But it relies on simpler, single-precision numbers just to calculate rotation, to save memory. This raw data is the absolute source of truth before a single pixel ever hits your screen. It is pure, structured text.
Moving right along to part 2, the graphical pipeline. How do these raw text vectors actually become a visual, three-dimensional world?
We really need to understand this translation process. The game engine actively bypasses legacy OpenGL rendering and uses a super-efficient modern pipeline instead. First, the coordinates are parsed. Next, a buffer builder formats that raw data, mapping out positions and textures. And finally, the tessellator uploads it all directly to your graphics card as a vertex buffer object, or VBO. The whole point of these VBOs is eliminating bottlenecks. Every single time your CPU has to talk to your GPU, it costs precious time. By compiling the data into massive vertex buffer objects, the system minimizes that communication overhead, which is a total game changer. It allows the engine to render thousands of blocks in a single, massive draw call, rather than asking the GPU to draw them one by one. Okay, part 3, optimizing the mesh. Because even with highly efficient VBOs, drawing every single side of every single block is simply an impossible math problem.
Let's look at a worst-case scenario. Imagine a solid 8x8x8 chunk of blocks. If you use the naive, brute force method of drawing every single face of every single block, you are demanding your GPU render a staggering 3,072 individual quads for just one tiny cube. If you tried to render a whole world like this, your graphics card would literally just choke.
To fix this, we apply an algorithm called naive face culling. It scans the grid and simply asks, hey, is this block face touching another solid block? If yes, it hides it. You can't see it anyway, right? By just hiding those interior faces, that massive number plummets from 3,072 down to just 384 quads. We've instantly reduced our geometry by a factor of 8.
But wait, we can push the math even further using a seriously advanced technique called greedy meshing. This sweeps across the 2D cross-sections of the chunks, finds adjacent flat faces that share the exact same texture, and literally merges them together. It reduces the entire outside surface of that chunk down to just 6 massive quads. 6! It's incredible!
But in computer science, there is always a trade-off. As this comparison shows, greedy meshing saves incredible GPU power, boosting your frame rate immensely. However, the dynamic penalty is brutal. If a player breaks just one single block, that massive merge quad is invalidated. The CPU is forced to completely recalculate and remesh the entire chunk from scratch. Which brings us to part 4, the far lands collapse. What happens when the math finally gives up? Now that we've seen how strictly governed these algorithms are, let's travel to the absolute edge of the procedural universe. Procedural terrain uses complex equations, specifically 3D Perlin noise. To make elevation changes look natural, the generator multiplies your physical x and z coordinates by a constant scaling factor of roughly 171.103.
But here is exactly where the architecture traps itself. The game historically casts this specific calculation as a 32-bit signed integer. In binary math, that has a hard physical ceiling. It literally cannot store a number larger than 2,147,483,647.
So let's do some quick algebra. If you divide that massive 2 billion number by our 171.1 scaling factor, you get roughly 12,550,824. When you travel exactly that many blocks away from the center of the world, the Perlin noise calculation exceeds that absolute 32-bit limit. The code triggers a catastrophic integer overflow, violently wrapping around from the maximum positive number straight into deep negative numbers.
And this mathematical rupture creates the infamous far lands. It's an absolute digital ruin. The deterministic rules of geometry just completely shatter. The terrain generator gets so confused by the overflow that it spits out these towering, grid-aligned walls of Swiss cheese stone, shattered dirt, and floating oceans. The math has completely lost its grip on reality.
Oh, and it actually gets worse. If you somehow manage to travel even further, you hit what are called the stripe lands. At the 25-bit limit, floating point numbers lose so much precision that the mathematical gaps between the numbers become larger than the width of the blocks themselves. The physics engine simply can't calculate your position accurately anymore, and you just fall right through the ground. The physical world, mathematically speaking, literally ceases to exist.
It leaves us with a truly profound realization. As these incredible digital systems transition from raw text vectors into explorable 3D geometry, they are ultimately prisoners to their own architecture. It proves that even the most limitless, procedurally generated horizons must eventually succumb to the rigid, inescapable laws of mathematics. It really makes you wonder, if these massive digital universes have a hard-coded edge where physics just break down, what undiscovered mathematical boundaries are holding together the very fabric of our own reality? Keep wondering about that, and thank you so much for joining me on this explainer.